How was the examination? Fun? Like writing an article? No, just like reading the articles. I only asked for brief answer, so yes, if your brief answer is correct, I give you a full score very easily. And I already grade one problem. It was not bad. Okay, it was not bad at all.
Which one?
The first one, of course, the spinning and velocity in every direction. Yeah. I'm expecting that the score will be announced soon. Soon. For my part, only for my part. Unfortunately, my part has the lowest score, so it might not help at all. All right. On Friday last week, we talked about mass transport. We talked about two kinds of phenomena. Molecular transport and bulk transport. Okay, molecular transport can be calculated using fixed law under assumption, under strict rules that fixed law can be applied only for binary system. And we also derive molecular transport using a general relativity, the relative velocity of the species. At the end, we got this equation. This equation is combined flux of A equal to molecular flux of A and convective flux of A. Okay? And this equation is represented in terms of molar basis. We can represent a flux of mass in two bases, molar basis and mass basis. Okay? And as I said earlier, it is more convenient for us to use molar basis simply because if our system is gas, we can apply the ideal gas law in molar basis easily. And if we have reaction in our system, then the reaction is also represented based on mole stoichiometry ratio. All right, so today we will start talking about shell balance. As I said, there are several problems, couple problems associated with this equation. First is that in this equation you have Na in both sides. So therefore you need to rearrange the equation before you can plug it into the shell balance. The second problem is the existence of Nb over here. So you need to know Nb first before you can rearrange the equation for Na. And I will give you several examples how we can deal with the term Nb. Okay? The first example is this system. Suppose we have a cylinder that at the bottom I have a liquid A. If this liquid A is water, for example, and then on top of this cylinder, I have a stream of air flowing across the opening of this cylinder. Air is considered as component B. A here is moisture. Remember, A is water. In air, you have moisture as well. So the stream of air that's flowing across this opening contains both A and B. All right? If your stream of gas is somewhat saturated with moisture, liquid here can be hardly evaporated, right? Whenever you have humid air, the water can no longer evaporate it according to equilibrium, thermodynamic equilibrium. However, if your stream of gas here has not reached saturated yet, then the liquid here can evaporate up there and be carried out from the system. If I want to know evaporation rate, that means how fast or how much of the number of moles of water A evaporated into this vapor phase per unit time, per unit area. I want to know the evaporation rate. How can I define the system? What should be my system? You have two choices. First, or you have three choices. One of them will be a poor one. First choice, this vapor phase can be considered your system. Second choice, the liquid phase will be considered your system. Third choice will be both of them combined. Everything within the cylinder will be considered as your system. Which one is easiest? If I ask only for the evaporation rate, how do you define the system? This is crucial in how you solve the problem. This is very crucial. So how many of you think vapor should be your system? Please raise your hand. Just vapor. Vapor should be your system. How many of you think liquid is supposed to be a system? Liquid phase. The rest? How many of you think everything within cylinder is supposed to be your system? What about? Okay. Who doesn't know? Who doesn't know? All right. First rule of thumb. Do you know rule of thumb? Do you know the meaning of the word rule of thumb? Rule of thumb means something common, like common sense, okay, or your engineering sense. The first rule of thumb says, never ever take two phases in one system. We always define system to be one phase only. Okay? Whenever you see the problems that contain more than one phase, define system to be one phase only. For each calculation, we must do it around the system in which there is only one phase. So either vapor or liquid phase supposed to be our system. All right? Now, which one would be easier? Or which one can be done? In this case, since we are in transport phenomena, we normally looking for the system in which we have a change in velocity, change in temperature, or in this case, change in concentration. Which phase should have change in concentration? Do you think concentration of A in liquid phase change with respect to position? Do you think concentration of A in vapor change with respect to position? If you do, then it is more convenient for us to set the vapor to be our system. Okay? Because every time when we talk about transport phenomena, we talk about driving force, right? 2 points in your system that has different in concentration would be driving force for mass transport. So whenever you see 2 points in your system like this, the concentration here and there is supposed to be different. So therefore there will be concentration, there will be mass flux in the direction from high concentration to low concentration. From that mass flux, if you integrate it all over the cross-section area, you can get the mass flow rate. Okay? So in our case here, our system would be the vapor. That's our system. Now, if we want to find evaporation rate, normally it is unavoidable that we have to calculate concentration profile first. Okay, so suppose I'd like to see concentration profile of species A in vapor. Let me ask you a simple thing. Do you think concentration of A in the bottom here and at the top here, which one is higher? Concentration of A at the bottom or at the top opening, which one is higher? Bottom, right? So therefore you imagine that the flux of A is supposed to go up. If I say the vertical direction is Z, normally we set up the axis to go to point in the same direction as our flux. So C is going up, okay? So here would be our C1, here's C2. What's supposed to be our shell? What does it look like? We are going to do a shell balance. What does it look like? It's supposed to be something like this, right? Here. This is our shell. In order to set up shell balance like this or shell like this picture, what should be the assumption? What should be the proper assumption for this kind of shell? First of all, you need to assume that concentration of A does not change along the cross-section area. Within the cross-section area, concentration of A is supposed to be uniform. Otherwise, there will be flux in radial direction, right? So as long as you have uniform concentration across the cross-section area, then your shell can cover the whole cross-section area. Suppose the thickness of the shell would be delta Z. So first assumption would be uniform concentration of A across the cross-section area. Okay? So if you set up the shell balance, normally for mass, it's just like mass balance. Mass going in minus mass going out plus mass generation by reaction supposed to be 0. Okay? So we are going to have in minus out plus any generation equal to 0. Remember, we can have generation term as long as we consider only one species and as long as we consider molar basis. If you consider mass basis in overall balance for all species combined, generation term becomes 0. Okay?